Hello everyone, good evening. Welcome back to the solutions for BSDS sample paper 2024. And now we were looking at question 18. Question 18 might appear to be a simple sum based on limits, but it's actually a bit more because it will allow me to show you a few formulas that we can learn from this. Alright. So first of all, what is the series in the numerator? The series in the numerator is nothing but limit. If I write the entire problem, it's sigma a to the power k, where k runs from 1 to 10, and then it's divided by, okay, instead of k we had n here, right? So let me rewrite it as n by n to the power 11. This is the entire sum, right? So we are just summing all of the powers till 10. Now we can evaluate this quite easily using a formula which is known as Fallbauer's formula. Alright, Fallhaber's formula. So let me show you that formula. Fallhaber's formula states this is if I show you the formula, you will feel like this is tailor made for this problem. This is known as Fallhaber's formula. This works for any power sum. So it will be like sigma k equal to 1 to n, alright, k to the power p for this type of series. So this sum will be represented by 1 by p plus 1 sigma I equals to 0 to p. Remember the limits. I equal to 0 to p. This is p plus 1 I. So these are the combinatorial terms. bi, these are known as Bernoulli numbers. Okay, and then I have n to the power p plus 1 minus I. Right, now this might look a bit confusing, but if you expand it with the conditions that we have been given here, it will be quite easy. Alright, so bi are known as Bernoulli numbers. These are quite widely used in physics, etc. I'll give you the first three values. You only need to remember those because most likely you will only need the first value, which is b0. Alright, I'll give you b0, b1, b2, b3. You can search it up yourself among how to generate these numbers. Alright, so there is a process for generating these numbers. It is usually done by this Fallhaber's formula itself, where we adjust the value of the variables to get b0, b1, b2, etc. Alright, so I'll give you the value so that you can remember it. Basically the first value is 1. Alright, so it will be quite easy for calculating, and you will see that this problem is practically tailor made for it. Alright, the first Bernoulli number is 1, then minus half, then 1/6, then 0, etc. Alright, so I'll give you that list, but before that let's see what the formula becomes here. So for this particular problem I can put p is 10, right? So p will be 10, and if I put p equal to 10, then our sum becomes k equal to 1 to n, because this goes up till infinity, right? I have k to the power 10. This will become 1 by 11 sigma I from 0 to 11. I have 11 I bi n to the power 11 minus I. See if you could follow the process of substituting the formula. Alright, now this is our numerator, right? I have written our numerator in terms of this new formula. So once I have done that, there is also one more component in the entire sum, which is dividing by n to the power 11. So if I divide by n to the power 11, you can see that only the coefficient of the leading term will remain, right? So let me explain this to you. Now limit n tends to infinity. If I have this thing, it is basically 1 by 11. I have sigma I equal to 0 to 11 I bi n to the power 11 minus I, and I'm dividing it by n to the power 11. So the first term when I is 0, right, that will be 11c0 b0 n11. Alright, so I'll start with, let me keep 1 by 11 outside. If I show you one term, you will understand. The first term will be 11 0 b0 n to the power 11. Then I have, okay, let me write it in the line below, that will make showing it a bit more easier. Alright, so the first calculation line, limit n tends to infinity, 1 by 11 stands outside, and I'll have, let us put I equal to 0. So 11 0 b0 n to the power 11 plus 11 1 b1 n to the power 10, and so on, this will go on. Okay, I have n to the power 11. Now you know that when n tends to infinity, the limit only evaluates to the coefficient of the leading term. Okay, because if I separate this into partial fractions, for the second term onwards, I'll have the larger power of n on the denominator. Okay, so the second expression turns out to be n to the power 10, and the denominator becomes n to the power 11. So as n tends to infinity, n to the power 11 will grow much larger, and n to the power 10 will lag a bit behind. So if the larger part is in the denominator, as n goes to infinity, that part will be 0. Similarly, for all of the terms upcoming till we reach 11 minus I, right? So we should be reaching a constant at the end. Till that part, everything is 0. So only the coefficient of the leading term remains. I hope you know this shortcut. If n tends to infinity, then if there are polynomial powers of n, the coefficient of the leading term becomes the answer if they all start with the same power. So n to the power 11, n to the power 11, right? If the degree of the polynomial in the denominator is greater, then the limit will tend to 0. If the degree of the polynomial in the numerator is greater, then the limit will tend to infinity, because it will grow much larger. If their degrees are same, then the coefficient of the leading terms, the ratio of the coefficients, will be the answer. Okay, now here we have 1 by 11. So this is basically 1 by 11 limit n tends to infinity. Okay, if we evaluate this limit, our answer will be limit 1 by 11 11 c0 b0. Right, now 11 c0 is 1 and b0 is 1, so 1 by 11 will be the correct answer. That is option B. Alright, please remember this formula. I have showed it to you, and I have showed you the implications of this as well. You can pause the video and note the formula down. This will be useful in this particular case when this sum seems tailor-made for it. Alright, any other method that you apply for this will become a bit tedious. Alright, though this is very niche problem and a very rare application of this theorem. Okay, now as I told you, I'll give you the Bernoulli numbers, the first few. Maximum will be needing up to B3. Alright, so make sure you note this down and remember them. So B0, as I told you, is 1. B1 turns out to be minus half. B2 is 1/6 and B3 is 0. Alright, I suggest if you have time within the preparation scope for exams, then you just look into how we generate them. Alright, either you generate them via computer programs, or you put specific values of coefficients and relating terms in the original formula, and you get each term to be 0 to calculate these terms. Right, so look it up. If you feel that you are still unable to understand, please put that in the comment section. We will make a small video on this theorem and its applications and the generation of Bernoulli numbers as well. Alright, so this was a sum that appeared quite easy, but it wasn't if you didn't know this formula. Alright, so there are some tricky formulas here. Now once you know that these type of formulas exist, you will try to seek them out for similar sums, and that will make your life quite easy. Alright, so there will be some sums like this in which if you know the way to approach it correctly, you will answer it quite fast. Otherwise you have to apply a lot more complicated techniques, and that might lead you to wasting a lot of time. All right. So I hope you could understand this question. If not, do rewind it and watch it slowly. And if you have any further confusion relating the Fowler-Eber's theorem or the Bernoulli numbers, put them down in the comment section. If needed, we'll make a video on that. All right. It'll be a very niche topic, so a 5-6 minute explanation should be enough. Okay. So question 18 is done, and I will see you all in question 19. Bye.